Hi, I'm Arya. I represent Group 9. My other group members are Xiong Ying and Prashant Madi. Our group is titled The Reconnaissance of Distributed Feedback Laser Diodes. So, the project overview, the contents of the project of this presentation is the principal objective of the presentation, which will be presented by me. The background theory presented by Ying, the technical approach, the 3D profilometer measurements will be also presented by her. The Silvaco simulations part will be presented by me. The tasks of each team member will be presented by Prashant. uh, Ying will present the progress made towards the result data, and Prashant will conclude by presenting the remaining work. So here we have in this project we are working on a 14-pin DFB laser from OptiLab using 3D profilometer. We first measure the structure, then we measure the IV Cara and power wavelength measurements. Later, Silvaco simulations were carried out of the 2D gain region, which was expected to match the measured Cara. We are looking forward to do the SEM simulation to obtain thickness of the gain medium and electrodes to put in the Silvaco simulation. At last, we write up the report. I'll hand it over to Ying.
Okay. So some quick backgrounds about the a laser. For a laser to work generally, it needs a gain medium and a cavity. And so this is what it looks like. You have a gain medium and also two mirrors on the left and right hand side of the gain medium. And then the gain medium is pumped by some method, either by electrical method or optical method. And for DFB laser we're handling here is pumped by electrical method. And the emission along the long axis cavity is reflected back through the gain medium. It's just between here and here. And the spontaneous emission photons stimulate further emission from the medium, which is, so this is the spontaneous emission, and this is the stimulated emission. Now, one of the mirrors is usually partially transmitting to allow some of the laser radiation to escape so that it can be coupled to a fiber optic. And so for the basics of a DFB laser, so this is the DFB laser we're mirroring here. So generally it contains the top contact, it's the top electrode, and then you have the grating, which is on top of the active layer, and then we have the substrate and the bottom contact. And the reason why people are interested in DFB lasers is because of its low noise and narrow spectral bandwidth, and also the high beam quality. Well, the key to the DFBs is the addition of a grating structure to above the active layer of the laser. And the combination of its refractive index and the spacing of the grating structure serves to reflect only a specific wavelength of light. So light traveling in the active layer is going to all directions, and so eventually struck the upper surface of the active layer and hit the zigzag. And this way the grating will reflect only a specific wavelength back into the cavity, but allow the others to pass through. So in that sense, we're able to have a single mode laser where the emission peak is under 1 nanometer as the DFB laser compared to the traditional fiber pro laser where you have a lot of modes inside your laser. So this is a picture showing a comparison between a single mode laser like the DFB laser and the fiber pro laser. And so the technical approach we have in this project is first we measure the component of the laser in the 3D profilometer using Zygo, and then so the optical profilometer uses the optical properties of the light to compare the optical path difference between a test surface and a reference surface. Instead of optical, so inside this profilometer, a light beam is split, reflecting half of the beam from the test material, which is passed through the focal plane of the microscope objective. And the laser performance measurement, firstly we did it by using a power meter, which we input different amount of current and then measure the output power of the laser. And then we're able to measure the spectrum performance of the laser using an optic spectrum analyzer.
So coming to the Silvaco simulation part, shown here is the structure of a FP laser with indium phosphide layers of different doping and a gallium arsenide active lacing region. The lacing region sits between the N and P type indium phosphide layers. A cathode is placed at the top middle part of the structure and an anode at the bottom. Using Silvaco simulations, we were able to get the photon density. This is photon energy plot. The photon energy peaked at 1550 nanometer, that's 0.799 electron volt, which was the same as the measured result of DFB laser. And we were also able to get a power versus gain plot with similar trend as the measured result. We are still working on adjusting the gain medium, cavity length, etc. to tune the plots. I will hand over to Prashant.
So coming to the task which we have, so the literature study of the DFP lasers, I have done the literature study and shared the information with the teammates. And the laser diode, the observing the laser diode using the optical microscope, Ying has been able to do it in her lab, and she also was able to do the characterization of the laser, including the IV and output power wavelength measurements. And getting the height of major components of the laser diode was done in ASU lab using the 3D profilometer. And we are thinking to possibly disassemble the laser diode in order to look from the side, so that we would be able to get the medium thickness of the gain medium and put it into the Silvaco for simulations. So we were still deciding to assign the tasks for that. And Silvaco simulation for 2D diode, Arya and Ying work closely in order to get the simulations done, and we are still working on that as well. And writing the report and giving the presentation we have worked all together, and writing the report I would be taking suggestions from Ying and Arya, and I would be completing the report path. And coming to the progress, the all the tasks which we have specified are in track except for the Silvaco simulations, where we still need to run the simulations and get better understanding of the results. And the wrapping up of the report and presentation time, we are doing it in the coming week for writing the report. And I would give to Ying for further.
Thank you. For the current progress, the first thing we're able to do is to observe this thing, the photodiode, and the microscope to tell what components we have inside the diode. So the first thing we have is a photodiode to be able to measure the output power from the laser, and then we have the DFB laser itself, and then the optical isolator. And then with that we also measure the components and the 3D profilometer with the photodiode and also the DFB laser. And so also we're able to measure the laser emitting spectrum, which is shown here. As you may see, this is a single mode laser emitting at roughly 1554 at 22.6 degrees. And also we measure the power versus current, which is shown here at 20 degrees and 25 degrees. As we see, the threshold of the laser is strongly affected by the laser's temperature, and typically the laser's threshold will increase exponentially with the temperature.
So coming to the remaining part of the project work, so we are yet to analyze the cross-sectional area using the scanning electron microscope, and we need to further edit the Silvaco code in order to get better understanding and try to match our measurement results. Based on the simulations which we do, we would further need to analyze the results, which is the pending part. And preparing the report is the last one which we are working now. We have already started working, and we would work in the next week to close it. Thank you.